Hi guys, Dr. J here, and I wanted to give you guys just a short little video about coordinate systems that will augment another video about coordinate systems that you guys will be watching. And you'll be able to find that video in my YouTube playlist or on Canvas for those of you in the Geophysical Field Methods course. So location, it's important, right? Location, location, location is the slogan. How do we know where we are? How do we know where anything is around us if we don't have a landmark or something specific that we're relating to? So we can say, oh, my friend so-and-so is 3 blocks down the street, or maybe so-and-so lives 2 miles down the road. But really, how do we know where we are unless we're relating ourselves to something concrete nearby? And really, it's very interesting because before about 50 years ago, when GPS was introduced originally, it could be quite complicated and in some cases quite labor intensive to determine your precise location, especially in the absence of landmarks, as I'm saying, unless you're saying, a certain distance down a road that everybody knows about, something like that. And especially in terms of determining your latitude and longitude, that has been a bit complicated in the past, and especially longitude has been quite challenging. Just an example here on the right is Hermann Wall's 1719 world map superimposed on a modern map, and you can see there's some variations there, especially in the longitudes. Now, for latitude, it is possible to determine that using your solar bodies. So you can, for example, use the position of the sun at noon when it's highest in the sky on the autumnal or vernal equinoxes. So in other words, when the sun is right at the equator, which happens either on the first day of spring or the first day of fall, you can use the position of the sun in the sky at noon on that day to tell your latitude. So as you can see, it's not even necessarily very simple to do that, although it's much easier than to do the longitude calculation. So it was really a big deal to try to figure out what your longitude was. This is a map this is Ptolemy's map of Europe, again superimposed on a modern day map of Europe, and you can see quite a bit of distortion. It's not so easy to determine your precise location at kind of this large global or even a regional scale. And this is something that was actually the subject of many competitions in the past. Governments offered prizes for people who could determine your longitude to a certain degree of accuracy, and really wasn't until relatively recently in history, 1500s on land, and even later than that, 1700s at sea, where you could begin to start to estimate your longitude with any degree of accuracy at all. One aspect of this is that you have to have an origin for your longitude. Now, latitude kind of makes sense. We can use the equator as our zero latitude. 0 degrees latitude is at the equator. That kind of makes sense. But what about longitude? It's a little bit arbitrary, and so actually the prime meridian that is most famous is the one in Greenwich, England, goes through Greenwich, England, and you can see here actually an image of the building where there's a laser used to mark the actual location of the prime meridian. Now it's actually a little bit, again, can be a little bit ambiguous because of your reference frame, whether you're using a geoid or an ellipsoid as your shape of the Earth. We've talked about that in other parts of the class. The Greenwich meridian is based on using the geoid. The ellipsoid, the 0 longitude line for an ellipsoidal model of the Earth is a little bit different. So that's a little bit of a complication again, but we've sort of specified this arbitrary location, Greenwich, England, as being the place of 0 longitude on Earth. And again, it's 100% arbitrary. We could have picked any longitudinal meridian, but as I say here on the slide, it's kind of a historical thing. So most of the world's navigational maps used Greenwich, England as their prime meridian, as did the US. And so in 1884, more than 100 years ago, an international delegation voted to make it official, and it's been the prime meridian ever since. Now, one of the other things that we'll talk about in the class a lot, and something that you all should be aware of, is that any coordinate system, as we've said before, has to have an origin point. You have to have a unit of measurement, and you have to have an origin. And one thing that's often very useful, for example, in geophysical surveys or any type of local survey really, is you can use a local survey. And in that case, you simply specify a location as your origin point. there really doesn't need to be any significance to that origin point other than for your local survey, you define that to be the 0, 0 location. And this is just like what we're used to in XY Cartesian coordinate systems. You have some point which is designated as 0, 0, and all other locations are measured relative to that point. And you can imagine just sliding this graph around on the screen, and it doesn't really matter as long as we're only concerned about positions relative to the origin. It doesn't matter the absolute location of this graph on the screen, where that's at. Sometimes what we can do is we can actually tie a local coordinate survey to a global reference frame by defining our origin point, our local origin point, to coincide with a point of known location. And so we can tie a local survey to a global reference frame. And in fact, this is kind of like what a UTM coordinate system is. So the UTM coordinate system defines many grid boxes across the whole Earth. And the idea here is that, of course, as we know, anytime you do a projection of the spherical Earth onto a flat map, you'll introduce some distortion. And so we can try to minimize that distortion by basically setting up a whole grid of origin points where we divide up into very narrow bands of longitude. So the width of each of these boxes only encompasses so much longitude, so the longitudinal distortion is minimized. And then if we just look at one particular box, we can make measurements relative to some local origin, and there are different types of UTM systems. But basically we have this whole grid of local coordinates where the coordinates of the origin are then specified with respect to the global system. So again, a little bit of a simplification to say this, but UTM is kind of like a global grid of local coordinate systems. And so you have to identify in a UTM coordinate system, what is your grid node, what is your UTM zone that you're in. And there are different types of UTM systems. This is one example, which is probably not so common, but you have the zone, the UTM zone that you're in. And in this case, you sort of have the lines labeled. And so your local origin is just the corner of that, in this case, maybe a 1 kilometer square box. And so you have your reference point, your location that you want to measure is relative to your reference point, your local origin, and then that origin is specified using some grid notation. That's kind of one example of a UTM coordinate system. This is probably not the most common one. The most common one is probably where we measure distances in meters relative to the equator, and then distances in the east-west direction is measured in reference to an origin which is 500,000 meters west of the central meridian. So if you take our UTM grid, our local system that we're working in, and you take the center of that grid zone and you measure 500,000 meters to the west of that, that's our origin point. Now, why is this done? This seems kind of weird and arbitrary, and it is arbitrary, but the idea here is that we never have a negative distance in that case. So all of our distances are always sure to be positive. One type of coordinate system, we've defined a local origin and we measure all of our distances in this grid relative to that origin. Same idea as all of the rest. So just a few things to take away from this short video. One, it's been very hard to define latitude and longitude in the past. Before the advent of GPS, we had to do lots of work to get those measurements that we needed. Two, you can set up a local coordinate system if you're only, say for example, you're doing a geophysical survey in some local area and you don't really care about the global coordinate system. You just want to know, where is this survey in relationship to my building footprint, for example. You can use a local coordinate system. You have a 0, 0 point, which you just designate to be some arbitrary point, and it doesn't matter what that local origin really has no meaning other than that you've just defined that to be the 0, 0 point for your survey. And then we can tie that local survey to a global system by referencing our origin point to the global coordinate system. And so this is something like what UTM does, where we have a grid of local origins, which we can then define our points in relation to. The thing about the UTM system is that we have many different zones across the whole world. And so in order to know your location in a UTM coordinate system, you have to specify both the zone and then your easting and northern coordinates with respect to that local origin. Okay, so just a few quick things for you guys to be aware of. We'll talk more about this in future videos, and I will see you in those.